Welcome to our Design Day presentation. We are Team 24049, the creators of the Localized Temporarily Deployable Autonomous Navigation Network, or LTDAN for short. We're sponsored by Raytheon and RTX Business. Our sponsors are Renee Van Alstyne, Jeremy Radke. I'm Kevin, joined by Carter, Richard, Eric, and Joshua. Today, we're excited to showcase how our project tackles critical challenges in autonomous navigation. Our multidisciplinary team, composed of talents in software engineering, electrical engineering, and systems engineering, has undertaken the ambitious goal of creating a proof-of-concept network. This network consists of 4 nodes that, through advanced signal processing techniques, including the integration of neural network models, enables accurate localization without the need for satellite signals and GPS. Our journey began with the detailed system design, where each component was meticulously planned to ensure robustness and functionality. Here's our system block diagram, which outlines the architecture of our network of nodes and receivers. The technical data package, or TDP, includes all specifications and blueprints guiding our development and concept to prototype.
All right, now we're going to go into the engine that allows for localization in this project, which is the signal strength and noise neural network. And we're going to understand via some artifacts how it was trained and how it is used in order to localize an unknown object. It should be noted that at the beginning of this project, it was a collaboration with UML where we were going to use time difference of arrival in order to localize the unknown object. But because of differences in semester in terms of when we are on break, they're on break in the year end, we've decided to go in 2 different directions as to have a deliverable that was capable of localization for Design Day. So getting started, we can see a distance distribution. So this is the data that was collected and how much data was collected. And this is the data taken from the very first training session. There were 4 training sessions in total. This is the first one, and the data was collected by placing a transmitter at the bottom step of Old Main and walking a kilometer down Old Main and having a script collect RSSI, SNR, and GPS coordinates in order to understand distance. Next, we've got feature importance. The feature importance here tells us that RSSI is more important than SNR in predicting the distance. SNR is still valuable, just not as valuable as RSSI, which will be evident here in the next plot. So here we have all the variables as a function of each other. So we have RSSI as a function of RSSI, RSSI as a function of SNR, but the ones that we care about are RSSI as a function of GPS distance, so this top right one here. And we can see a trend, which is what we would want to see in creating a neural network like this. RSI and SNR are correlated. Most likely this is the importance, or why we see an importance of SNR. And then SNR and GPS distance, there is a trend here, but you can see how this is going to be less useful. So now, after we've put all the training data into the neural network, we've trained it, and we're evaluating it, you can see its predicted versus actual distances. So this was trained in a scenario where you would walk in a straight line. So imagine a line here going through the middle. You can see it's pretty accurate up to a distance of 400 meters, and then up above it, its accuracy will fall off a small amount. And then here are residuals. Residuals tell you how much error there was at a distance. So we can see again, the residuals are very close to 0 up until 400, and then past 400 they get larger, and you see these deviations and points of extreme. But this tells us that the model does a very good job at predicting distance to 400 meters, up to 400 meters. All right, now let's take a look at the GUI, which is going to give a good sense of all the functionality exposed to the user. Now, on system start, some initialization will be required, and that is the number of nodes in the network. We'll choose 8, and the size of the network, that's one size of the square, and once chosen, it'll give you an overview of the network layout and how you should position each node in the network, and where each node 1, 2, 3, 4, should be positioned for accurate results. Upon entering the system, you'll have 2 options: checking the network health. This will just allow you to see how data is reflected here in real time, and then the color coding will tell you the relative strength of each signal reception. So minus 91 here is an example of a weaker signal, minus 66 here is a stronger signal. And then here's the meat and potatoes, the visualization. Clicking on this will allow the user to see the predicted position versus the actual position here. So you can see we've coded on an emulator the T-beam to provide RSSI and SNR values from a large data bank that is a circle. around the 400 by 400 meter network. And each update here, the RSSI and SNR values are taken into account, run through a sum of least squares localization method, and then projected here on the UI. There is a good amount of geometric dilution of precision. So where the object or unknown object is in the network, the estimation may be better or may be worse. And you can see here the error and then the average error of our trip so far. You can toggle the lines to just see where the estimated location is, and then you can export all of the data recorded by the GUI to a CSV for later analysis.
Rigorous testing is vital. Our team has performed extensive tests to validate each component's functionality and the system's overall performance. These procedures ensure that our system meets all operational requirements, preparing LTDAN for deployment in any environment. Our results in testing have been promising. The LTDAN system achieves a positioning accuracy within 1/5 of the area of the network. Through risk analysis and mitigation strategies, we've addressed potential changes, enhancing the system's reliability and effectiveness.
Alright, so in terms of the hardware for our project, it consists of three main components. We have the anchor nodes, the receiver, and the information display. So the system operates with anywhere from 4 to 8 anchor nodes, and those consist of a T-beam Supreme device, which sends LoRa signals at 915 megahertz. It uses a SuperBat omnidirectional antenna to send those, and is powered by an 18650 battery. It contains 3D printed housing, and once again, there'll be 4 to 8 of those. For the receiver, the actual device which will be taking in all of those signals, it uses the same basic hardware with a T-beam Supreme device, a SuperBat omnidirectional antenna, and an 18650 battery, except this one contains a Pelican case, which is a bit stronger than the 3D printed housing. The information display, which will receive all of the RSSI SNR values from the receiver and process them in order to determine location, will use a T-beam Supreme device and SuperBat antenna to receive the signals and then pass them to a Raspberry Pi 4, which is powered using a power supply using 18650 batteries. It'll be displayed on a Raspberry Pi touchscreen device, and all of these signals will be transferred using USB to micro USB and USB to USB-C cables.
So in conclusion, we came a long way to get here with several changes to our project methodology from the RSSI to TDOA and then back to RSSI for the final product. As of now, the LTDAN system is finally passing all of its requirements that we got from the sponsor. So now that the software and hardware are fully integrated, our plan for the short term is to focus on continuously improving accuracy and range until design day. Also, we believe that the existing system will provide an excellent starting point for future development by the sponsor or potentially by another team in the future. Our recommendation for future work is that the project gets a phase 2, which could be integrated with the existing TDOA work by our team and by UML using their hardware to improve the accuracy of the system.